Hello everyone, welcome back to the channel, and I'm here again with divisibility related topic in number theory, and I will be discussing divisibility of powers of 2, because all of them kind of have a very similar behavior, and sometimes you might be remembering them as properties for 2, 4, 8 or so on, but in general for any 2 raised to the power k where k is a positive integer, so this is a general power of 2, and all of them are the divisibility behavior of these factors are pretty similar. So I'm going to kind of demonstrate that here. So firstly, I will take a number n that's a general positive integer. What we've been doing so far, it is a positive integer, and I'll take this n, is any number, any positive integer on which I will test for divisibility for all these numbers. And I will introduce a notation that's a common notation. I'll say that if that n is divisible by 2, then I write it as 2 divides n. If it's divisible by 4, I write it as 4 divides n, and so on. If 2 raised to the power k divides n, and that means n is divisible by this factor, leaving a remainder of 0. So I will write that as 2 raised to the power k divides n. These are just notations, so once again I'm going to remove this part because I need some space to describe n. Now I will write n in its decimal representation, something I've done in multiple videos of number theory. We'll try to link them as usual. So this is a generic form of n, where n is a j plus 1 digit number. So n looks something like this. We've done this in multiple videos. 3, a2, a1. This is how the number looks like, but this is what the value of n is when expressed in powers of 10, because 10 is the base of a decimal number system. This is the last digit, this is the last but one digit, this is the third last digit, and so on. But here, I will write some extra terms here because that would help me prove the divisibility, or rather derived more general expressions for divisibility. So instead of writing 10 raised power 3 here, I'm just writing 1000 directly. And instead of writing 10 raised to power 2 like this, I'm just writing 100 directly. And then 10, this is just 10. And then the last digit is a0. So this is a general n. I don't need this part, we already know this. And now I'm interested to know if this n is divisible by, or rather, what types of n are divisible, or if I can look at n or the digits of n, and if I can just understand the divisibility by just looking at digits without really doing the whole division for a large number, that becomes much easier. So I will start with writing n in different forms. We'll take 10 outside as a factor. This becomes 10 raised to power j minus 1 and j minus 2 and 100 a3 plus 10 a2 plus a1. All of them have a factor of 10. It's important to remember that 10 is exactly divisible by 2. But I will be left with a0 outside the last digit that doesn't have a factor of 10. So effectively, I can say that since all of this part is divisible, it has a factor of 10 and 10 is divisible by 2, I can as well write it as n is congruent to a0 mod 10. So n when divided by, sorry, not 2, n when divided by 2 leaves a remainder of a0. So when I'm saying 2 divides n, this remainder has to be 0 or divisible by 2. Because if you have 2 mod 2, that's effectively a remainder of 0. Either 0 or a factor that's divisible by 2. So in that case, if a0 is any one of these values, then 2 will divide n. That's the divisibility of 2. So sometimes we say it as a number, a positive integer n is divisible by 2 if the last digit, a0 is divisible by 2. And for that to be true, it has only 5 possible values, that is 0, 2, 4, and 6. And as we know, commonly we say these are even numbers. When a number ends with these digits, we call it even. So because they are divisible by 2. So for 2 was kind of straightforward. I'm going to do this for 4, and for 4 I write it slightly differently. It's n. So instead of taking 10 here, I'm going to take 100 here. Why am I doing that? Because 100 is divisible by 4, 10 is not. So if I take something that's divisible by 4 as a factor here, it gives me insight into the remainder that comes out. Straightforward here, it's a times j minus 1 plus dots plus, I took 100 out, so it's 3 plus, I've taken 100 out, so I'll just focus on this part. That means the last two digits. So because 100 leaves a remainder of 0 mod 4. So if I say that 4 divides n, it means that 4 has to 4 has to divide the remainder exactly. That means n should be congruent to 10a1 plus a0 mod 4. And if 4 divides n, then I should have this should leave a remainder mod 4. Remainder 0 mod 4. That means outside this 100, where 100 is divisible by 4, we should have this part that should be exactly divisible by 4. So that means in words we can say that this number n will be exactly divisible by 4 when its last two digits are divisible by 4. So a1 and a0, if it's the form of something like a 24 or 60 or 80, whatever be the other digits, I don't really care. I don't really need to look at how large the number is and what the other digits are. If the last two digits are divisible, give me a number. If the last two digits give me a number here, if it's 24, it's 2. A1 is 2, A0 is 4. This gives us 10 times 2 plus 4 is 24, and is mod 0 leaves a remainder of 0 mod 4, then it is divisible by 4, and I don't really need to look at anything else. And then we're going to do this for 8 because we are hoping to see a pattern so that I can generalize something for 2 raised to power k. And so this was for 2, this was for 4. For 8, I'm going to take 1000 outside because 8 divides 1000, and now you can see why I wrote it like 1000 here, because I wanted to get here. Simply repeating exactly what we did for 2 and 4. For 8, I'm going to write a3 plus 100a2 plus 10a1 plus a0. So now I have to look at the last three digits because 8 divides 1000. So since 1000 mod 8 is congruent to 0, then n is congruent to this whole term. Then a1 plus a0 mod 8. And then for 8 to divide n exactly, that means if we can say n is divisible by 8 when this remainder is exactly divisible by 8. Perfect. Do we see a pattern? Yes, we do. When it's 2, so 2 is 2 raised to power 1. When I'm checking for the divisibility of 2, that is 2 raised to the power 1, I am taking only one digit from the end. So I'm only looking at one digit, the last digit. When 4 is 2 squared, I'm looking at the last two digits. And because 8 is 2 cubed, I'm looking at the last three digits. So you can see exactly where I'm getting at, right? 2 raised to the power 3, I'm looking at the last three digits. So for 2 raised to the power k, no matter how large n is and no matter what the digits are, I just need to check if the last k digits, the k digits from the last, are divisible by this, then we can say that n will be divisible by 2. 2 raised to the power k. So that will divide n if the last k digits, the k is obviously less than or equals j. If this, if 2 raised to the power k divides this, it's kind of where we got from here, but we can end it right here, but I would really like to look at some examples of some big numbers to kind of understand how all of this is useful. So I'll need some space to write down big numbers. Because you don't really use divisibility for small numbers where you can directly look at it like a 50 and you can say that hey, it's divisible by 2, it's not divisible by 4. You're not really looking at 50, you're probably looking at numbers like 50 million, 60 trillion. In such cases, if I take a real example of n like 5, 6, 7, 4, 3, 9, 8, 5, like a really big number, huge number. This is a positive integer. How many digits are there? So there's A0, A1, A2, A3, A4, A5, A6, A7, A8, A9, A10, A11. It's an 11 digit number. So J plus 1 is 11, that means J is 10. No, sorry. It's a 12 digit number because J is 11. This was AJ. So it's a 12 digit number. Yeah, it is. So the last digit is 4. It's very easy to see that when 2 divides this, 2 divides is equal to 4. So 2 divides n. Now if you write n as something like what I had written as taking a factor of 10, you will see something like this. Is just to show ourselves how the number looks like. Plus 4. So this is a0, and this is how I had 10 and I had something in brackets. This 0 comes from that 10. It's just a real number to demonstrate the general form we have written. We don't really need this, but I can also write n as, this is just for clarity. the properties are done as plus 64, or I can write 60 plus 4. Then I get this form 10 times a1 plus a0, where a1 is 6 and a0 is 4. So what's that? Then this is 64 is divisible by 4. So I can say that 4 divides n because of this reason. I'm gonna do this for 8 again. So 3, 6, 4 would be expanded like this. This is 100 times a2 plus 10 times a1 plus 4 plus a0, sorry. a2 is 3, a1 is 6, and a0 is 4. So this is pretty interesting here. So 100 times a2 plus 364. What is this mod 8? I got to divide this mentally. So 32 gives me then 44 divided by 8 leaves a remainder of 4. So this is clearly not divisible by 8. So we can write it like this. 8 doesn't divide n. And I'm just gonna end this with 16 here, because beyond 16 it would be a bit hard to divide. So is n divisible by 16? Good question. So k here is 4, as I written. So I need to look at the last 4 digits of this. So I will say that n, or 16 divides n, if 16 divides the last 4 digits of n, that is this. Is this true? We're gonna find out. So this thing, when divided by 16, because 128 is a multiple of 16, so then we are left with, oh sorry, I made a mistake here. This should be, because it's not this form, this is already with factoring 10, the actual number was this. So 128 is a multiple of 16, so we are left with a remainder of 84, and 84 when divided by 16 gives me a remainder of 4 again. So 16 doesn't divide, and you can kind of solve this mentally very fast. Let's look at this huge number and find out its divisibility is 16. Now, using some more modular arithmetic, it might be possible to predict, like say for example, the divisibility of 64 from the divisibility of the previous factors of 2, but that would be a bit complex and involved, so I'm not gonna get there in this video. But this is where we'll end at. So I hope this was really useful. Thank you so much for watching, and thanks for always being with me. Thank you so much.